Hello everyone. In behalf of my team, this is the presentation of our study. Artificial intelligence is revolutionizing industries with changes like voice assistants, autopilots, autonomous coding, and even cancer detection using CT scanning. An artificial neural network is a computational algorithm that attempts to model the brain's processing capabilities and corresponds to a set of layers of activated neurons, as shown in the illustration. The output layer, located at the end of the neural network, contains as many neurons as the number of objects to be identified, and with the information propagated from all the previous activations, it assigns a confidence value to each neuron for the prediction of a class. In particular, the first layers of the network are responsible for the extraction of low-level characteristics, such as color, shape, orientation, and others. With a greater number of hidden layers, the architecture adapts to more complex features, giving us a better understanding of the information of the database that we want to learn to identify. In particular, an artificial neuron is the elementary unit of an artificial neural network. This can be understood as a function that considers all the outputs of the neuron from the previous layer. The information in each neuron is interpreted by the activation functions, such as the sigmoid function described in the image to the right. This allows us to discriminate whether the neuron with the collected information is more or less relevant for the activations of the following layers. Convolutional neural networks are the evolution of the artificial neural networks, and they meet the need to capture spatial information in images and videos. This type of architecture extracts the information by applying filters with the help of convolution, delivering appearance characteristics by reducing the number of parameters to be processed. In particular, an image is reduced and vectorized to be analyzed with an artificial neural network as described above. In this way, we have a function called neural network that, with the appropriate weights and biases, decipher the input information and predicts a class. Considering that we have a database with information of a system that relates an input to an output, we seek to quantify how the neural network is predicting each element of a class using an error function that delivers a low value when the network performs a prediction close to reality and a high one otherwise. The average values of the evaluation in multiple elements of a database are known as the cost function, represented by the letter J in the images. And the main objective of deep learning is to find its local minimum based on the weights W and biases B. In particular, we look for the negative gradient of the cost function that defines the direction towards the minimum, considering a learning rate that determines how much the optimal point, moves between one iteration and another. Now, let's get to know the PAMELA-UANDES database. It was built with the simulation of an underground subway station in the city of London in 2008. It contains 15 videos in which the heads of the people have been manually annotated for each frame. The videos are divided into 8 boardings and 7 alightings, considering a door opening to a width of 80 centimeters. In total, there are 119,000 labels made manually to pedestrians of all videos, of which 49,000 were used during training. In addition, each individual has been assigned a unique identifier in the database, allowing the quantification of the results with tracking metrics. Transfer learning is the art of using trained models to solve deep learning problems. An architecture that has been trained in its own database seeking to identify a specific class can be reused for the identification of objects that share similar characteristics. In particular, for this version of the software, 2 architectures are presented for the extraction of characteristics: YOLO v3 and Faster R-CNN Inception v2, pre-trained in the COCO database that contains information on more than 200,000 tagged images between 80 categories. Given the similarity of the information with the PAMELA-UANDES database and its size, the models are refined by initializing the weights and biases with the existing information from the previous training, reducing the network training time. Each model has a cost function that fits to its architecture, and training stops when its value stops decreasing. This avoids overfitting the model to the database, making it unable to recognize new images. The training is constantly evaluated in 3,000 images, associating 17,000 labels never seen by the network, balanced between boring and alighting. This maximizes the average precision of the detection that measures the ability to find true positives over the total number of positive detections. The evolution of the results during the iterations that were detailed in the previous graphs are reflected in the demonstrations, where YOLO V3 to the left surpasses Inception V2, using less training time, fewer iterations, and reaching a higher average precision. Now, let's talk about object tracking. In its simple definition, tracking can be understood as an estimate of the trajectory of an object while it's moving freely in a plane. This is a process that includes the identification of the subject in an image, assigning him an identity that remains until he leaves the scene. For the detection of multiple objects, a Markov decision process was used, as described in the illustration, which covered the state transitions of a detection. The initial state of any classified pedestrian is the registration. With this, the coordinates are associated with an unique identifier. In this way, a subject can change to be tracked if he is affiliated with a new successful positive detection, or to be disappeared with a new wrong positive detection. The target remains tracked as long as there are no associations in consecutive frames that meet the requirements of distance or intersection over a union, or it can become missing in situations such as occlusion, loss of detection, or abandonment of the scene. An object can be kept in a missing state for a predefined number of frames and can be tracked again in the event of a match, but if an identity is missing for a considerably long time, it is permanently deleted. Now, due to the cardinality that the association of identities of a large number of targets can mean, the Hungarian algorithm was used to determine if an object in the current frame is the same as the next, providing a distribution of identities. In the illustrations A and B, the tracked objects are shown in the frame n and the detections in the subsequent n+1, respectively. In C, the distances and intersection over union between all the elements that are used to minimize the association problem are shown. Finally, in D, a new tracked object with identity 3 is found alongside the association of 0 and 1 with the detections B and C. And also, ID2 is lost because it exceeds the maximum allowed distance with its candidate A. In the tables, you can see the resulting cost matrices and the optimal allocation of identities according to the Hungarian algorithm, minimizing the distance or maximizing the intersection over union. The Kalman filter is an algorithm used to estimate the dynamic state of a system in the present, past, or future. In general, this is a Bayesian system, where a sequence occurs between two states, one of prediction and another one of update. The Kalman filter was used on each identified subject to predict their position, producing identity changes and erroneous deletions. In general, the bounding boxes estimated at a time t are obtained based on those at a time t minus 1, considering Newton's equation of motions to define the current position based on the velocity and the previous position. This estimate is updated with the time t detections, considering the noise and uncertainty of the information. And the Kalman gain is the constant that determines the inclination to believe more or less in the measurements and predictions. Thus, the detections delivered by the convolutional neural networks are supported by the Kalman filter that provides an estimate of the positions and the size of the bounding boxes for the identities in the missing state, reducing the noise introduced by the detector. The general system is described in the illustration, where the association of new identities is reflected through the Markov decision process in conjunction with the Hungarian algorithm, according to the criteria of distance and intersection over union. Identity assignment is a process that allows you to keep track as long as there is a prediction or a detection for the association in a consecutive frame. But since the system can have changes of identities and loss trajectories, counting the number of passengers, it is not simply reduced to count the number of identifiers assigned. To carry out the definitive passenger count, limits were defined, as can be seen in the illustrations. When the centroid of a tracking detection coming from the platform exceeds the threshold of the subway door, the pedestrian counter increases by 1 and marks the tracking as counted, since the subject is already approached. The same way, to count the number of passengers leaving the scene, it is considered that the tracked object can take 3 directions, so that when the centroid intercepts with any of the defined limits, the counter is decreased by 1. Both in boarding and alighting, the system has a wide and sufficient tracking area in which you can detect and assign an ID The results are presented below in the best configuration of the YOLO B3 algorithm. Considering the system with an association criterion by intersection over union with a threshold of 30% and a permanence of the missing identities of 10 consecutive frames, in blue we can see the tracks identified with the prediction of the Kalman algorithm, maintaining an identity thanks to the Hungarian algorithm. In red, the detections of the artificial neural network can be seen as a comparative. The operation of the detection and the tracking algorithm is verified by evaluating 6 videos never seen before by the CNN, evenly distributed between boarding and alighting. Let's consider the following metrics. True positive represents a correct detection associated with a tracked object. A false positive that represents an incorrect detection associated with a tracked object. A false negative that is a label in the database that is not associated with any tracked detection. A fragmentation that corresponds to a database path that is found and is being tracked, but it is temporarily interrupted. A change of identity that is generated when a known trajectory of the database changes from one identity to another due to the proximity between two traces. And finally, mostly tracked and mostly lost trajectories that corresponds to a subject whose path is recovered for more than 80% or less than 20% respectively. These parameters can be seen represented by the precision, recall, MOTP, MOTA metrics that are used in competitions such as the MOT Challenge. Accuracy represents and measures the ability to find true positives out of the number of positive detections. Recall measures the ability to find true positives over all the database labels. MOTP corresponds to the sum of the intersection over union between the actual bounding boxes with the detections for all the frames in the video. These average by the total number of the matches made. This metric demonstrates the ability of the tracking algorithm to estimate positions of objects independent on their ability to maintain a trajectory. The MOTA, on the other hand, corresponds to a measurement of the precision of the tracked objects, considering the number of false positives, misses, and identity changes over the sum of the real labels in all of the frames of the video. To determine the behavior of a tracking algorithm, it is sought to increase the precision, recall, MOTP, MOTA as much as possible. The best result were obtained by combining YOLO V3 with the tracking algorithm, delivering an average precision of 97% that considers the number of true positives over the number of hypotheses of the system. And on the other hand, the precision of multiple object tracking, MOTA, supports that in 81.7% of the cases, the system did not have any errors of false positives, false negatives, and identity changes. In addition, the detected bounding boxes had an accuracy in their MOTP estimate of 73.3%, considering that the intersection over union with the bounding boxes. The tests were carried out on 6 videos that, of a total of 234 people, 233 were counted. It is considered that different architectures learned successfully to identify the subjects of PAMELA-UANDES, and one of the main reasons is that the characteristic extracted from a higher perspective consider a lower complexity than a full body view. It is expected that future versions will consider a database that allows learning in different situations of luminosity, perspective, opening the way to new tools applying in different areas, such as generation of proximity alerts for pandemics as COVID-19. Thank you.